So while we wait for newcomers, I'd like to tell you a joke. I'm Michał, by the way. And if you want to hear a functional programming joke, you will have one. Why did this chicken cross the road? Do you know it? Do you know it? Who knows this joke? Functional programming Haskell joke. One person over there. Okay, that's cool. So why did the chicken cross the road? I don't know. Why? Well, it's very simple, really. The best way to understand it comes from the idea of contravariant functor. As you probably know, a functor is just a mapping between categories that respects the category structure, a homomorphism, if you will. Now, some constructions that we want to express look like functors, but in some sense turn morphism around. We call these contravariant functors. As you have probably noticed, we can indeed define a contravariant functor as simply a covariant functor on opposite categories, invoking the obvious correspondence. Of course, you have already noticed by now the obvious connection this has with the category theoretic generalization and so on and so forth. So this joke was a very popular one last year, and I think it makes perfect point because we are learning functional programming starting from theory because the power of math is what we are using, right? But humans don't work like that. They don't really learn like that. They learn by practice. And this is the talk I want to show you today. So very, very practical. Theory may come later or on some different talks or books or articles. So this talk is fast and functional, two talks in one. The functional bit is about a microservice that we will build. And it will be in Scala, but it will be a very, very modular one. It will be so modular that we'll be able to plug and play different modules and see how they work, how performant are they, and how they work together. And the second component is fast, and it has two meanings in this talk. The first meaning is performance, like the application performance, the one that we are creating. And we'll be using flame graphs to show the performance of the microservice that we create. And the second meaning, because we have a very, very modular system, modular application, is a development speed, right? If we have a very, very nice modules with boundaries and constraints on them, then we really have separation of concerns. We can develop faster because we know where we are. So this is the talk I want to give you today. And by the way, it's very practical because it's how we really develop services at our company, which is Reality Games here in Krakow. And even the beginners in Scala are doing them in such a way. That's why I started with a theoretical joke to show you that you don't really need to start like that if you don't want to. So let's do it. The application that we will create. This will be for marketing people. So imagine that your IT department is tasked with some tool to help marketing people see their product campaigns. And all days were that the TV commercials or billboards were the most prevalent ones. So the campaigns were very, very analog. But these days, the products, if you have a new product, you probably have to go with the influencer campaign. That means that you are buying some time, like product placement time, with the YouTubers, right? The very popular ones with lots of followers or people on Twitter or Instagram. So you have one product, and then you do some contract work with those YouTubers that product place and influence the people that are following them. And of course, if you are doing this kind of influencer campaign, you will have like YouTube video or Twitter or Instagram, lots of them, and each of them has its own statistics. But what you like to have is to have a holistic view of all the items, influencer campaign items, how they behave for this one particular product. So this is the tool that we are going to create, a collection of items and just aggregating the statistics of each particular video. So a very, very simple service, collection of videos, how many likes, how many views. We'll just focus on YouTube for now, but it will be a generic one, so you can plug in the Instagram, Twitter, and so on and so forth. 3 requirements. The first one is ability to add and update collections. So if you have a collection for product X, you just need to list all the YouTube links that is connected with this particular campaign, right? So a very simple CRUD thing. You need to update collection, have a state internal in the database, whatever is that you need. Second requirement is your application needs to be able to fetch YouTube videos using the YouTube API, right? So you have this video ID, one of the items in one of the collections, and you need to get how many views, how many dislikes, how many likes, and so on and so forth for each particular video. So this is the second requirement. And the third one, you need to be able, for all those videos, those items, you need to be able to aggregate them into one collection of influencer items statistics. So a very simple application that we can show and use really. So it's practical, but it's also a simple one, so it fits one talk. Of course, we have also a non-functional requirements. Usual ones: web server, HTTP client, collection storage, and logging as an example of metrics or anything like that. So cross-cutting concerns that we all need to have in our applications, production applications. And of course, we are on a functional conference, and functional programming is programming functions, but also what we would like always to have is kind of a separation between what's pure and what's impure, what's side effecty, right? And from the requirements I've shown you, you can just deduct that calculate stats, the one that gets stats of each particular video and aggregates into one is a pure function, right? Pure, no side effect at all, just one function in and out. But the rest of them, saving collections, fetching YouTube, is all a side effect kind of module. So let's see how we can handle this kind of applications, which are mostly what we've been working in many industries. So Scala, who knows Scala? So that I'm aware. Cool. So you probably already know that case class is just a data class. We have 3 of them in our model. The collection of videos, right? So list of string is just a video ID. Influencer item is just one particular video statistics. And the collection stats, of course, the aggregated ones. And this is our pure logic. This is the function that we implement first because it's our core logic and also is the simpler one, the simplest one. And we'd like to have functions like that in the whole application, right? But we don't because we have those nasty side effects. So a very, very simple function. Items folding, we are folding over the items and getting the collection statistics. So impressions are just views, and score is just engagements plus likes, things like that. So let's say it's a business logic, right? Just one function, nothing too magical. So we have a collection of the statistics, and we get out the pure value. So after this double colon collection stats means that the function returns a collection stat, one pure value. Easy to reason about, easy to test. It's very, very fast. So we'd like to have something like that, pure win. But we have also some other requirements, right? We need to get the collection. Having this collection ID, we need to get what kind of videos are in this collection. So is it a database? Then we need to have a very, very large side effect. Maybe we need to also fetch something from YouTube. For sure we need to. So this is another side effect after getting those videos. So we have a sequence of operations that we need to do. Get collection using collection ID. Then we need, from this collection that we just fetched, we need to get those videos out. And for each video, we need to call YouTube API, right? And then we'll get these statistics and finally call the pure function that we just implemented, the calculate. And of course, we need to put some logs in between. And because it's a sequence, 1, 2, 3, 4, we need to have this for comprehension, like do notation in Haskell, so monadic sequence. One operation needs to end before the next one can be executed. So we need to have something like that. And what should we use? What have been we using in our application? So future, for example, right? So we can have this return value. Return value can be a future. So it's a kind of a monadic looking. It can be using for comprehensions, and we can do all those things like getting collection from the database. We can get we can fetch statistics from the YouTube API. But what's wrong with the future? Apart from not being functional, which is not very like the practical example, right? What's wrong is that it's too powerful. It will make our lives miserable in several months. In this case, when we return future, we allow others, including ourselves in 6 months, to do anything future can allow us to do. So it's very, very powerful. That means that maintenance cost of this application will be bigger. And maintenance is all we really do, like 90% of the time. Right? So we write it once, but then we maintain it forever. So future is too powerful to use in such case because we just need very few functionalities. Maybe I/O, it's functional, right? In Scala, the cause effect and other effect systems, very, very popular last year and the year before. So we can use something like that, it's functional. But I think the argument is exactly the same like in future. It's too powerful, you can do anything in I/O. It's still very, very close to shooting yourselves in the foot. When you are doing a maintenance or a bug or a new feature, you can do anything. So you are not constraining yourself here. That's why we are doing something opposite. We are doing this type F, which is nothing and cannot do, not nothing, but cannot do anything at all. So it's not too powerful because it cannot do anything. That's why we use something like that. And we just say in this signature, after the double colons, we say what kind of features this type F needs to have. And it can be a feature, can be I/O at the end, but the user chooses it. So it's a constraint, right? We are very, very constrained. Yeah, this is a constraints library. This is a nice, the discussion we've been having for a few minutes now is a very, very nice idea to constrain yourself as often as possible. There's this nice talk by Runar from Scala World. I really, really recommend you to watch it. It's about just that. If you care about maintenance, you need to make your pure functions as constrained as possible. You need to just use those things that you really, really need to use. You need to follow the principle of least power, right? So this idea again. So we'll be using F. Colon monad means that F has this flat map and map, and we can use it in for comprehension. So that's all. That's all we really need for now. So let's go back to the 4 steps we wanted to do. First step is we need to be able to fetch collection out of somewhere. We don't care where from. We just need to fetch it. So we just add this collection view algebra, and which is our thing, which I'll show you in a bit. And we call this fetch collection function on it, passing the collection ID. And we get a collection back. So this is how a collection view algebra looks like. Again, very, very simple one, no implementation. We are doing this in this effect type F and nothing more. So just semantic, nothing really telling us what's underneath, like from the accidental complexity point of view. The second step is videos, right? This is the equal sign. We don't have to have any additional effect because we have this collection already in the second step. We can get video out. And then, for each video, we need to call the YouTube API. So our type F needs to have this YouTube fetching functionality, video client functionality. And again, we don't care how it's done. We just say we need something like that. And if we have something like this, like the next feature, the next very, very small block of code, very, very small algebra, then we can finally do something like that, yield a pure value based on the pure function that we implemented so far. And that's all. That's all the logic that we need for our application. And it looks like that. 4 lines of code for all the requirements to be passed. And we are still in the pure world. Of course, we need to add some logging, but exactly in the same way. So just adding logs in between, and but the mechanics are exactly the same. So logging algebra, right? So we just created this function, fits on one slide with all the logging and all the things. We don't care how it's done. We just say what should be done. So functional programming at its core. And what we've achieved is that we moved some of those side effecty things into a pure world, into effect things. So we have those algebras that are moved to the light side of the force, And we have this getStats algorithm, which is also pure. That means easy to reason about and easy to test, right? But still, we need to have those side effects. And those side effects are in the interpreters, the bad world, the bad guys, side effects, all-powerful things. You can shoot yourself in the knee this time, but you know where you are in the code based on whether it's interpreter, whether it's on the future or I/O or something like that, or whether it's F, it's pure thing. And you can't do many things with F other than what you just declared. Algebras versus interpreters. And that's the basic idea how you do modularity using this technique in Scala. For video client, just an example, I just show one of them to not bore you to death. But this is how it looks. So you have this algebra I've shown you, which was used in this getStats. And for HTTP, it looks like that. So it just does one single request. So again, this is impure world, one interpreter, but one block of code, one module. And HTTP doesn't leak anywhere outside of this one. Right? It doesn't leak. So it's used, but it doesn't leak. Again, one slide. And it's kind of a boring one, right? So we'd like to write boring code. And I implemented several interpreters for each algebra because we want this plug and play thing, right? We will be doing plug and play. So I implemented HTTP client, Hammock client, which is a purely functional layer on top of Apache or anything you want, but we'll be using Apache. HTTP4S as a client. For collection view, we'll be using two in-memory data stores. One of them is based on linked list. The second one is on trimap, for performance reasons. And the logging also, one of them is like default, logs everything. Second one is more aware of what's being logged. So it's logging only up to 1,000 logs per second. So let's do this plug and play then. Second part. Before we continue, I need to warn you that what I'm about to do should not be done in production. It's on my laptop. YouTube is Dockerized, not the whole one, but the API is Dockerized. So we can do those kinds of performance tests just on the server, on the service side. We'll be using WRK. Who's familiar with it? Some of you. So this is the line of code in the command line I will be putting in. It means that we'll be using one thread out of 4 or 8 possible on this laptop. We'll have 16 open connections, and we'll be doing as many requests as possible to the server in the duration of 30 seconds. As many as possible, right? To kill it, to do whatever. -- latency means that we also want this latency report, so we'll see how the service behaves with different modules plugged in. Async Profiler is a JVM thing. It attaches to the Java process and probes what's happening on the CPU right now, what's happening on the CPU right now, what's right now, 100 times on second, and it will generate this flame graph for us. So we are doing the test on our service, and we are probing what CPU has been doing, and this kind of nice diagram, nice flame graph will appear. Who is familiar with flame graphs? How much should I talk about? Okay, a bit. So flame graphs should be read from the bottom. The bottom line is like the function that's always there, main, right? So it's entry point, you are always on the CPU in the stack. But then this main function calls another function, which is a bar on top of it. And the wider the bar, the more samples, or the more time, you can interpret that like that, more time the CPU spent in that particular function. So obviously what we are looking for, we are going bottom up, and we are searching for the pieces of code from our package, so the code that we wrote, that takes a lot of time. And we'll see such a code because we'll do some performance analysis on the version that we just created. So version 1, HTTP on server and client, logging all the things, and we have this in-memory linked list state. So let's see how this looks like. This is the flame graph that we'll generate, but before, let's just see the code. Okay. So here's the code that we've been implementing, and here's the main function where we get all the things injected together. As you can see, logging is here, collection view is here, video client is here. So we just have those one line of code that we need to declare what kind of interpreter are we using for this particular algebra, and that's all. So this is the default setting that I've just shown you, and now we can try to performance test it. I've already run one performance test to warm it up. What it's doing is just adding like thousands of random collections into the application, and then runs this test, the WRK I've shown you, 30 seconds, 1 thread, 16 connections. And what we can do is we can run the profiler JPS. We get this thing here, and we just run the profiler. So the test runs for 30 seconds. This profiler probes for 10 seconds, 100 times a second, or 99 times a second. And then afterwards, we just get a new shiny flame graph. And I will do this only once to show you how the process looks like. And that's basically all. The flame graph looks like that. This is the SVG file. So it's interactive. So you can click on those things here. I will make it bigger. You can click on those things. So all, as you can see, 93% of the samples were in the fork join worker thread. So usual stuff in Akka HTTP server. So we are going up and see what other functions were called. And up here, we can see there's this function, one function that we have here, get inference result. And we're going up and see what's the last one from our code that was called. And this is the default logger info, which was like 56% of time. So obviously, after doing this kind of 20 seconds test, 30 seconds test, we already see a bottleneck, right? The logging takes like 60% of the CPU time. What about the results then? Results are done in this kind of way. So we have this latency reports. For 99th percentile latency, we have average latency, and of course we have number of requests that we've been doing. So this is the report. I have a nicer looking version of it, which looks like that. So the first run with all those default components, in 30 seconds, WRK managed to do 8,000 requests and a half. 99th percentile of latency was 82 milliseconds, and we managed to do like 280 requests per second. And we learned that the logging function took a lot of time. On the side, the 70% here was 56, right? But a lot of time, majority of time. So let's see what we can do more. We can replace the logging interpreter. Just one line of code needs to change. Just one line of code needs to change. We don't have to change any logic. We don't have to change getStats function. We just change one line of code. The logging from default to the dropping one that doesn't log more than 1,000 logs per second. This is just one piece of code, one module in one file, and we can run another set of tests. And when we run it, exactly the same as I show you, we get like 10 times better performance, right? 89,000 requests just by replacing the logger. Just one line of code changed, and we get almost 3,000 requests per second with nice statistics like 99th percentile of latency, 62 milliseconds. And this service is really doing the HTTP calls. So then we get to look at another flame graph that we just generated, right? And we can see that this time it looks a lot different because we changed one line of code. And the bottleneck, the most time the CPU spends in our code is this Akka HTTP video client, 20% of the time. So it's still a lot. It's something for us to hold on to. So let's change one line of code, again, from Akka HTTP into Hammock, Apache-based one. Again, you've seen the interpreter for Akka HTTP. The Hammock one is very simple. It's just a different library, but it's still just one line of code changed. And we get a little bit better performance, not really that much. And 3,000 requests per second. I think it's better than before, but not substantially, right? So we see that even though we changed the whole Akka HTTP into Hammock, we didn't get as much performance gain as we like to. And the flame graph, how does it look like? It looks like this Hammock thing is eating 54% of time of the CPU. So we see that the problem is still there. The majority of the code is running using these HTTP calls, right? Because, well, let's face it, our service is doing nothing really that much than calling the YouTube. So we see that it is a bottleneck. So we need to approach it differently. So what can we do? We can add this caching thing. And we can do that by changing just one line of code without any logic, without anything more, because we have all those side effective things in the one interpreter that we want to use. And after just introducing caching, we get this huge amount of performance boost, right? 9,000 requests, 900,000 requests, 62 milliseconds latency on 99th percentile, and it gets into 31,000 requests per second. So it's a lot. It's a nice service then. It can take a lot. It's one instance can take a lot. And how the flame graph looks like. How does the flame graph look like? As you can see, it's the whole one. We'll zoom in a bit. The flat thing in the bottom right corner. How does it look like? It seems like it takes a lot of time. If you look closely, it's a MISC unsafe part. What does it mean? It means that the CPU is waiting for I/O. Our service is very, very heavy on I/O. We can see that just watching at the flame graph. So it's waiting for the I/O operations to finish. So there's nothing really much we can really do with such a flame graph. But if we have this opportunity to do just one line of code change, and then we have like 30 seconds test to see the performance, why not change the whole server, right? Just for fun. So don't change the logic, just change the server from Akka HTTP into HTTP4S. Again, one interpreter out, one interpreter in, just very, very small module. The rest stays the same. And we get 1 million requests in 30 seconds. That means that we have 38,000 requests per second for our small service that has the YouTube and has some caching layer. And the average latency is very nice because it's in microseconds, right? And 99th percentile is also very nice. Less than 10 milliseconds is what we like to have. So a very, very fast service written in Scala, written using a purely functional way. And the flame graph looks like that. As you can see, there is a nice division between different lines of code. No special bottleneck. You can of course go into some concurrent implementations, like in the middle of this flame graph, if you want. Sorry for this technical trouble. Fortunately, I know that the lunch break is coming in 10 minutes or so, and whoever is fastest gets to it very, very quickly, right? So let's go to conclusions. Conclusions are about what we've done. So what we've done, we've created a small service. It's a really, really small service with lots of algebras. And we changed the infrastructure details just using this plug-and-play technique. And I think the most important thing is it's very, very simple functional techniques, basic functional techniques, right? Nothing magical, nothing category theoretical, just using some purity and immutability, referential transparency, those things, nothing more, just the simple things. And if we can really change the server implementation, HTTP client implementation, logging, video, and add caching with one line of code, and without changing the core logic or any tests, then we won very, very nicely, because we can develop faster and nicer services. So I think that the pure and impure thing can be very, very nicely separated in Scala code written in such way. So in the pure world, you have algebras with this F type. It's very, very constrained, and it's good for us. And it's very, very easily unit tested, and it's very, very fast. And side-effecty things are interpreters. So it's a very dangerous piece of code. And if you are in the interpreter zone, you should pay attention, because you can do anything with I/O, you can do anything with future, but you can do integration tests. And I want to show you how the integration tests of interpreters look in our code base. We are using test containers. Test containers, whoever is familiar with that. Okay, test containers can put your Docker container up in your test in Scala without you doing any Docker compose, Docker stuff. And the test, integration test with the YouTube API, which is Dockerized, fits on one slide of this presentation. So it's the whole test. What it does, it creates the container. The test containers are running the containers up, waiting for the port to answer, to be listening for us, and only then runs our test. And this is a test for interpreter of Akka HTTP client. As you can see, this is just calling this one function that this algebra has, and this interpreter interprets, and checks whether we get the video statistics back from the YouTube. If we have integration tests like that for each interpreter, and in our code base we do for some services, what we are doing is we are pushing each commit which is green to production. If we have tests like that and tests like property-based or any other unit tests for the pure stuff, then we are very, very, very sure about what's going to happen on production. So that's kind of a nice addition. We don't have to test any logic in the integration test. We're just testing the integration part, whether our interpreter really integrates well with this YouTube API. But we also have tests for Cassandra, for example, right? So interpreters for Cassandra with the particular production version of Cassandra that we are using in this kind of tests. So again, fast and functional. We can develop very, very fast things in Scala using this technique. We can have a modular code. We can see where we are in the pure world using algebras, impure world using interpreters. And we can do those plug and play things to see how the application behaves. The example in this presentation was about the performance, right? We can test the performance. We used flame graphs to see how the performance looks like. Of course, this is all on GitHub, and I prepared a README for you if you want to follow, because this is just theory. This is just me talking, right? If you want really to check whether you can have something like that in your own application, I encourage you to just go through this process here. See the code. There's very, very small amount of files, and not very big ones, and of course, nothing magical there. Just those things, the most important bits, the hardest bits I shown on the slide, so nothing surprising. And the whole README is just how to set up the whole environment and how to do things like that in the real HTTP microservice world. My name is Michał. This is my Twitter handle, so any feedback is welcome. Please shout out. And this is my blog, and thank you very much for your attention.
We have almost 10 minutes for questions.
Hello, how are you? Here.
Where are you?
Here.
Hi.
Great talk.
Thank you.
I enjoy a lot. This is more a philosophical question, perhaps because there is a lot of blogs going there about tagless final encoding, which is the technique you have implemented there, and MTL, which is not good for Scala, and free monads, and I wanted to know what is your opinion about that. If it's better to do it in tagless final, free monads, yeah, or MTL in Scala is not good, in Haskell, yes, but...
Well, thanks. I think that there's a lot of discussion about what's a good approach to doing services in Scala, and I think it's overwhelming for many people. It's just the amount of ideas and the amount of good practices which are changing every few months. It's not a good thing, to be honest. So what I'm encouraging you to do is to find the style you like, and if it's really working for you in your particular project, just follow it and do it, right? Just as we did with this one. And I didn't tell you, but we have the newcomers in Scala who are, or I did tell you, who are starting like that. So it's encouraging to me that you don't have to be a like functional fundamentalist guru in order to do any service or maintain any service. You can just start out having known only Python before and write Scala in this way. So that's why I like it. But you need to find your style. The ideas are there, but we need to have this separation. What ideas to follow and what not. That's my answer. Sorry, I don't have any more non-obvious. Any more questions?
Hi, thank you for the great talk. I think it's really important to talk about precisely those things. I was wondering whether you tried to maybe exchange the I/O implementation. So instead of using cats.io, I think, did you maybe try Zio, and what were the results?
So I used I/O here in interpreters, but as I told you, you can do anything in your interpreter, so you can also use Zio. I haven't touched it, but yeah, I think this should be another performance parameter, right? Could be. I didn't do it because I didn't want to do any flame wars about technologies.
Yeah, that's what I was hoping for.
Yeah, referencing the first question I got, right? And I think that this also doesn't mean that HTTP4S is faster than AK-HTTP. It's just faster in this particular case. I forgotten to mention that. So, and no flame wars about technology.
Very good point. Thank you.
Thank you. More questions? There was one over there.
Thank you for the great talk. And I wanted to ask, how would you go about introducing this functional, like final tagless style approach in a service that's already implemented on Scala Futures? And how would you combine those two, if it's even possible?
So refactoring is a lot harder than doing from scratch, a lot harder. So if you have a team that's already experienced in doing final tagless, those kind of technique services, then probably you will come up with a solution, and it should be just one. It should be discussed per case. But what I do is I would refactor out some pieces to the tagless final and just future it into the existing side effect code. I think that's a pretty normal technique to be for you to do. The only thing I think is the drawback of this is if you have lots of tests that are using those interconnected modules like integration tests and so on and so forth, you need to re-implement many of them in order to use this technique. But that's my only suggestion. Sorry again, I can't be more specific.
If I may add to that, I'd like to testify that it's actually very well possible to do that refactoring. We've done that in our chain. That's an open source project. You can look it up, and we've been doing quite a lot of refactorings, which would make various components of our code base return via the abstract F effect. So if you look for those comments in that repo, you'll find how we approach that.
So how experienced was your team, if I may?
I'd say quite experienced, and it was not. I'm totally with you. That it's much easier to do that from scratch than to refactor it, because all kinds of stuff happens when you don't have that discipline. So it was quite challenging, and I think all of us being a bit experienced, bit familiar with tagless final, I can now say that most of us are proficient with tagless final, and those kinds of refactorings. I literally can see how the team grew on that, on those refactorings. So that was a journey.
Thank you very much. Okay, we have some time for questions, but the dinner or the lunch is more important. So thank you very much. Catch me on the hallway and have a nice the rest of the conference. Thank you very much.